Hello everyone, welcome all on Data Phoenix webinar. Today we will speak about deployment AI models, and together with us Daniel Lenton. He is the CEO and founder of Unify, and he will share with us his expertise and knowledge of deployment models and how you can do it more better way. And I hope share his tools and how you can use it for your deployment. You can ask your question using Slando. The link is under the video. And I give the microphone to Daniel.
Amazing. Well, thank you so much, Dimitro, for that really nice introduction. Really great to be here, and obviously a big fan of the webinar series. Yeah, so as you said, I'll be going through today democratizing AI deployment. And what we'll do throughout the talk is talk a little bit about the fragmented stack in AI and all of the different levels that are going on and how they interact with one another. And by the end, we'll go through a few case studies and a few tips and tricks for how to optimize things, before then talking a bit about some of the things that we've got coming out later in the year. Well, not later in the year, things that we've got coming out early next year with Unify. Okay, so without further ado, let's get started. So the first thing that's worth looking at is the fact that so AI is obviously exploding onto the scene. There's lots of triggers that have, there's lots of moments you could look back at as being these watershed moments. There's AlexNet in 2012, which was the first time that we had really good performance on ImageNet with the CNN. There's been, the Transformers coming out in 2017. ChatGPT was a very big moment last year, of course, where it really got AI out into the hands of many people. But behind the scenes, there's been this slow burning increase in funding to AI over the past few years. And this is made clear by the number of rounds and the amount of funding going into AI infrastructure companies specifically over the last few years. Now, of course, this is a very good thing. We all want the field of AI to progress as quickly as possible. But the downside is that as many new tools come out, lots of these effectively end up competing to be the tool or the all-in-one approach, and you then end up with lots of different solutions to the same problem, lots of fragmentation and lots of incompatibility. And this creates a lot of noise and a lot of confusion, and this is not good when when you're trying to go out and use the very best tools that are out there, and you're cluttered and overwhelmed with so much going on that you really don't know where to start. And this is one of the problems that we're really looking to address with Unify. But before diving into deployment, I just want to say a few words about the importance of unifying AI research and experimentation as well. So the worlds of research and deployment are very different. The things you need to do when you're researching is to basically try lots and lots of models, try lots of new ideas, experiment with different architectures and different libraries and tools, and finding all the newest hot stuff on archive and composing it together. And this is where it's really important to be able to leverage any of the things that are out there interchangeably. And I'll talk a little bit about how we can unlock that potential with Ivy, which is the framework that we've built to address this problem. So again, the problem is that today you have your project, but your particular framework of your project only supports the particular libraries and models that are built for that particular project. So you don't have access to all of the amazing open source tools that are out there. You only have access to a subset of them. Now with Ivy, what we do is we enable you to take any version of any library or model from any framework and bring this straight into your project, all with one line of code, which really for researchers enables you to try new ideas at the speed of thought. So it might be the case that you are using PyTorch, but you would like to try DeepMind's latest model, which is implemented in JAX, and now you can bring that in. With relation to the latest frameworks, it might be that you want to deploy the latest PyTorch model on an Apple phone and bring it to XML. Well, again, with Ivy, we're working on our XML backend, and now you'll be able to take PyTorch models and convert it straight down to XML, ready for app deployment, etc. So for researchers, this is really an important thing to be able to unlock speed of thought, experimentation. And just with a couple of examples. So the first one is you can take an architecture, a model. So in this case, let's say that you are using PyTorch for your project and you would like to use DeepMind's latest JAX encoder. Well, now with one line of code, you can take that JAX architecture, you can transpile it to PyTorch and just slot this in to your broader PyTorch architecture that you then use for your downstream research. And again, this all just happens with one line of code. Similarly, let's say you're using TensorFlow in your project and you would like to use some computer vision functions. Well, unfortunately, TensorFlow doesn't really have that many good computer vision libraries. On the other hand, Cornea is an amazing computer vision library, which is only supporting PyTorch. Well, normally that would be a problem. You can't use it, and you need to just kind of go through the source code and try to kind of manually use the parts that you find. But now with Ivy, that's not necessary. With one line of code, the entire Cornea library, which is traditionally a PyTorch library, magically is now a TensorFlow library, and this is all on line 10. And now suddenly you can use this Cornea library in your TensorFlow project as though it was, as though it was a TensorFlow library originally. So again, making it very easy to experiment across the boundaries of these frameworks, all with one line of code. And just a few points on how this works is the first point is basically what we've done is we've built an intermediate representation at the functional API level. So we've created Ivy's functional API, which itself is a superset of the APIs of all of the existing frameworks. So that means it is much more generalized than any of the other frameworks. So if PyTorch supports, the argument transpose, and TensorFlow supports the argument flip dimensions or something, we would support both of those arguments in Ivy's function to make sure that it is the most general that it can possibly be. This in turn means that most of the time, our front ends, which are shown on the left, these are re-implementations of the functional APIs of all of the existing frameworks, but we re-implement these functional APIs and we mimic their behavior totally as a composition of the existing Ivy functions. And each Ivy function has a backend specific implementation where the Ivy function is expressed as a composition of framework specific backend functions. Now, the importance of Ivy's functions being very general is that in most cases, we can simply go from the front end function on the left, tf.math.cos, which is just expressed using ivy.cos, because Ivy's function is always, at least as general as the front end function, which then basically, aside from a little bit of casting logic, just defers to torch.cos. So it's, in many cases, it's a very simple one-to-one-to-one mapping when we go from, in this case, going from TensorFlow on the left to PyTorch on the right. Now, in some cases, it's not that easy, and there are certain functions that are supported in one framework, but not another one. For example, JAX has a function called topk. We implement this using Ivy's topk function before doing a little bit of, reordering the values in the indices and doing some casting on the left. And then in the PyTorch implementation, there is not a topk function, so we need to do this compositionally using functions such as argsort, index select, gather, and so on. So again, we can't always go one-to-one-to-one. Sometimes if something exists in one framework, we need to build it as a composition in the other framework in order to make the code conversion possible. So this is how Ivy does code conversions and how that's useful for research and experimentation. The next thing is, well, we thought, can we take this a step further, and can we use Ivy's transpilation capabilities to actually make models run faster? And is that possible? And our insight here was that all of these frameworks have varying support for the different compiler infrastructure. So some of the compiler infrastructure is very well supported by some frameworks. For example, XLA is very well bound to JAX and to TensorFlow, and it has pretty good support for PyTorch, but nowhere near as robust. OpenAI Triton has very good support for PyTorch, not really any support at all, for JAX and TensorFlow, although that is now coming. And what that means is a very quick way to unlock all of the compiler infrastructure, and by virtue of that, various hardware targets as well, such as TPUs through XLA. One way to do that is by doing transformations at the framework level itself, from PyTorch to JAX to TensorFlow, etc. And the idea being that then we can unlock all of the compiled infrastructure, unlock all of the frameworks, unlock all of the hardware, and find ways of improving the performance just by converting to different frameworks. And actually, we found this to be the case. So although it wasn't really what Ivy was initially designed for, we put it to the test, and this is on CPU. So taking PyTorch models. So each of these different shapes represents a different model. On the x-axis, we have the runtime speed. Sorry, on the y-axis, we have the runtime speed. On the x-axis, we have different point compiler solutions. And the vast majority of these are Torch. So with Torch Dynamo, there are lots of different ways you can compile Torch. And what we've done is we've circled the fastest version. And you'll see on the far left, there is TensorFlow and JAX. And this is the runtime performance when we do a transpilation and we convert the PyTorch code over to TensorFlow or to JAX and see what the performance is like. And this is by going through the approach I just outlined. And what we see is that in 3 of the 7 cases, TensorFlow was substantially faster than anything that PyTorch could do. So again, bringing substantial speed ups to models just by doing code conversions and transpilations. And we see the same on GPU. So again, the same graph, the only difference now being that it's running on GPU. And we see, again, many more of them. So 5 out of the 7 models. The fastest implementation, when we considered every single possible PyTorch backend, was JAX. And that's because JAX has very good support with XLA. XLA is a very sophisticated compiler architecture and give big speed ups. Now, what you'll see is that in most cases, the difference between the circled green point and the next closest is very marginal. You'll see that this orange star is not substantially lower than the next lowest star. So Torch is very competitive, but JAX just had the edge. And in some cases, it wasn't noteworthy. For example, with this one, which was Albert, it was substantially better. In the case of this blue one, Distilbert, again, quite substantially better, and so on. But the main takeaway is that actually PyTorch has done a very good job of closing the gap. A year ago, PyTorch was it was hopeless at deployment. I say that it wasn't designed for deployment. It's not like they were doing anything wrong. It was designed for prototyping and research, but there wasn't Torch FX integrated. There wasn't Torch.compile. There wasn't executorch. Torch Mobile was much earlier on. So really, it was just this global interpreter locked, bottlenecked Python code, like throwing pre-compiled kernels together without any operator fusion or without any graph analysis. And it was very, very slow. But PyTorch are closing the gap now. But still, translations and transpilations can give an edge over what's possible. But that then has led us to think more broadly, like, how can we unify? We've already worked very hard on unifying the frameworks. We've made it possible to convert code between these different frameworks so that they can empower researchers to find it easier to mix and match code when they're doing new experiments. Also making it easier for companies who are deploying with TensorFlow to connect to the broader PyTorch ecosystem, etc. But if we really want to empower people looking to deploy AI models at scale, what are the kind of things we can do to help in this space? And that's what we're going through today for the rest of the talk. But first, I think it's very helpful to paint a bit of a picture of the fragmented landscape. Well, very quickly, I'll first go through just what we'll be talking about. So I'll now give an overview of the deployment stack and how it's so fragmented, talk a bit about why the fragmentation is increasing, talk a bit about what typical deployment setups look like. So what kinds of tools you should think about using in what different kind of scenarios, and then talk a bit about some of the things that we're doing to address this problem and what we've got planned for release in the coming weeks, which is these 4, 5, and 6 points, talking a little bit about what we're doing in the space as well. So without further ado, let's dive in. So on a high level, we have, well, actually, this is the wrong slide. On a high level, I'll very quickly speak verbally to say that we have 4 levels of abstraction. There is orchestration, which are tools that basically spin up the different, how to say this? They basically provision devices and they handle the API requests and send those requests to the certain devices and spin these things up and down. There is then also compression, which is about making the model smaller and using various techniques to make the model both faster and lower memory. There's then compile infrastructure for actually extracting these models into efficient graph representations ready to be run by hardware. And then there is the hardware itself for actually running the ones and zeros and actually kind of, doing the computation. Yeah, sorry that this slide is wrong. Actually, if you go to unify.ai/blog and you see our first blog about the Cambrian explosion, there's a good image there that shows these 4 different levels of the stack. This is actually unpacking the orchestration layer, which we'll be going into now. So there's these 4 layers. Let's first look at the orchestration layer, which is what this image is showing. So within the orchestration layer, we have these sub layers, which are the infrastructure, orchestration, what we've termed like the container level, then model endpoints and model binaries. And I'll go into all these in a bit more detail in a moment, but just to talk a bit about what orchestration layer is doing, it's basically so what happens when you deploy a model is that typically you have API requests coming in that you don't have control of. You've put your model up there and it is being used it might be by end customers, it might be by other people in your company. If it's like an internal chatbot or something, it could be used by whoever, but you have no control of when these API requests come in. You might suddenly get 10,000 of them come in at once at a certain point in time. You might then get nothing come in for kind of several minutes, and so on. And you need to make sure that you're provisioning your infrastructure and your hardware and your models so that they gracefully scale up and scale down to the ever-changing demand that's coming in. And this is, in a nutshell, what the orchestration is responsible for addressing. And to just visualize this problem in a bit more detail, so basically, worst case scenario, well, there's lots of things that can be bad. It's bad, first of all, to have unutilized GPU capacity. So let's assume that the x-axis here is time. So as we go from left to right, we're evolving through time. On the y-axis, we have the capacity that we're paying for on an hourly basis to actually compute things. And it wouldn't be great if we've paid a lot of money and every hour we're spending hundreds of dollars on this massive GPU cluster that's hardly being used, and we have a few API requests coming through, and then there's nothing, then they come through again. So this is very bad. This is very robust and stable for the end user, but it's not very good for your CFO, who's going to be barking down your neck because you're wasting resources. On the other hand, you might under provision, and then you get a whole spike of requests, and then suddenly all of your users are left waiting, waiting very long time as their API requests are queued up, waiting for this limited set of resources that are trying to handle this big influx of requests that have come in. That's also not good. So in reality, of course, what you need to do is provision these things dynamically. So when requests start to come through more, you want to make sure you spin up more GPUs. When the requests come down, you want to scale down the GPUs you have available, or it could be CPUs or nodes or anything like this. So this is broadly the problem of orchestration. Now, the reality is there is not just one simple solution to this. The reality is the landscape, and this is, again, where we come to explain the image that I showed a few slides ago mistakenly. This is the right time to unpack it. So there's different levels of hierarchy in the entire kind of serving orchestration layer. There is, first of all, infrastructure. So this is kind of, I suppose, bare metal solutions, things like pure clouds, AWS, GCP, etc., Lambda Labs, and so on, where you basically get access to the servers as they are, and you can control everything on top. The entire software stack that sits on top of them is up to you. You basically get the keys to the hardware, and it's yours to do with what you want. And this is maximum, maximum flexibility. So this is what we're showing on the right. Very, very flexible, but very complex to set up. There's a lot of software that you need to build. You can then build, pre-written, and you should, in most cases, use pre-written orchestration tooling, things like Kubernetes and so on, and also other tools that have Kubernetes style infrastructure built inside of them, where you can then automatically provision up and scale down the nodes. This is, again, very flexible because actually Kubernetes is the standard in the field, so really everything supports it. So it's very flexible, and it's not as complex to set up. It handles a lot of this abstraction. It handles a lot of this stuff for you. And then there's kind of serverless server options as well, where aside from actually being able to handle the provisioning of API requests to different Docker containers, you can actually not handle the creation of servers at all, and effectively just have the tool that automatically spins up the devices for you with full containerized applications. So you don't even need to think about, if you're paying this amount per hour for a GPU, you just send the API requests in, and the software, the serverless GPU, will then spin this up and down for you automatically. And then at the highest level, when we get to the bottom, we have model endpoints and model binaries. So basically, in these cases, you don't even need to think about the Docker application or the Kubernetes or anything. You just effectively upload your model, and everything else is done for you. The whole environment is handled for you. You upload your model, it will be binarized and then set up to handle API requests, and you're ready to go. Now, the good thing here is it's incredibly simple. It can get spun up very quickly. If anybody's used Replicate, for example, it takes seconds. The whole kind of selling point is spin up your models in one line of code. So that's very good. And one of the downsides is it's very rigid, so you have very little control over the software stack used underneath, which means that there are some suboptimal decisions likely made that you can't cater for your application. And also something that should be emphasized is that it is expensive as well. So when you have a production grade application that's really scaling, you almost always want to have better control of your margins and actually get the GPUs provisioned yourself at the lowest possible rates, to actually then build the infrastructure yourself. Because with these things that are very quick to get started, they typically have a business model which is pay per compute, and as you start to get real production grade usage, that goes through the roof, and you're paying many middlemen for building the software that you could actually look to make in-house to control your margins a bit better. So there's this whole spectrum of tooling, from things that are really advisable when you're building MVPs and you're building minimum viable products and you're trying to just prototype quickly, and you should use the very simple things. But as you start to get your application more sophisticated, you should start to take more control both of your costs and the full flexibility of your stack, basically. So that's kind of in a high level, just the orchestration layer, and that's its own. It has its own inner nested hierarchies and a lot of complexity going on. And a lot of these tools are not compatible with one another, so there's a lot of decisions to be made about what you should and shouldn't be using for any given application. Now, the same is true for compression. So the next level in the stack, one level lower, is compression. So we then and within compression, there are various different techniques as well. So we have quantization is one approach, where we basically take all of the weights and we make them all lower memory. So for example, going from float 32 to float 16 or int 8 or even lower than that, and effectively we just keep the exact structure of the network, but all the weights get smaller. There's pruning, where we keep the weights the same size, but we turn some of them to 0. We find some weights that can be entirely removed. This is the next one that's reflected next along. We then have tensorization as well, where we effectively do matrix tensor decompositions, like singular value decomposition and so on, where we basically find a smaller number of free parameters for the tensor, and then these can be projected to the dense matrix, but actually the number of controllable variables is reduced, and you can optimize through gradient descent, for example, through these. And similarly, you can store this smaller number of variables in memory, so it reduces the memory of the forward pass as well. And then we have model distillation, where we basically take a large network that's been trained and has learned a lot of information, and we use the outputs of that network to train a smaller network. And the idea being that that you can learn a lot more from the conditional probabilities that are output from the large network than you could learn from the one hot ground truth training signal in the training data. So you kind of distill all of the internal representational knowledge from the large network into the small one just by training on its outputs, which is incredibly simple. Kind of surprising it works so well, but it does work very, very well. And this is a very important thing to consider for deployment, just because when you're deploying, often having the full model in full resolution is overkill. If you don't care that much about accuracy, and what matters more to you is cost, or what matters more to you is getting this squeezed onto a phone or something, then you of course need to start thinking about compression, because then it's only through doing compression that you can ever get some of these things running on certain edge devices or operating at a certain latency that's completely essential for your application and so on. So really an essential part of the stack when doing any AI deployment. And just going into all these in a bit more, so I'll share the slides with everyone. I mean, they'll be available online afterwards if anybody wants to dive in a bit deeper. But first of all, yeah, pruning is effectively removing some of these weights. So we can represent this as cutting the weights between the network. It's also visually represented here with the block having some bricks removed. It's the same kind of concept. And yeah, and it just reduced the size by turning some to 0. There's lots of different pruning approaches. So again, you can read about all of these, but the structured versus unstructured. So that's whether you take whole neurons, for example, whole filters versus just individual weights. It can be done randomly. It can be done based on the magnitude during the forward pass, doing it based on the magnitude of the activations and the weights is a better approach. But you do need the training data to do that. So random is a very simple approach where you can get some percentage reduction. But again, the accuracy drop is typically higher when you do it based on random weight removal. There's then kind of iterative approaches where you continue to where you pass the data through the network, you look at the magnitude of the activations, and then you prune some weights, and then you do it again, and the weights have changed based on the same inputs because some are now 0, and then you do it again, and there's you can do it from very, very iterative all the way to just doing one forward pass the network, finding the top, the lowest 20% weight activations and removing those, or doing it slowly. And again, generally iterative is better, but much slower, and one shot is obviously faster. And again, you can do it global versus local. You might have some heuristics that some layers are more prunable than others, and you can localize the pruning, or you can go for the whole network and so on. So a lot of different configurations there for pruning. So then there is, lots of libraries for doing this. So I won't go into all of them, but again, I'll share these slides afterwards. But suffice it to say, a ton of libraries which have their own unique algorithms, their own unique, compiler infrastructure and hardware that they work with, and their own unique features. So again, very complex to wrestle with all of this and to make sense of all of this, because there's not just one package here. There's many, each of which have their own benefits and their own supported packages that they work alongside. So another one is quantization. So this is basically where you're reducing the size of the bit size of the weights, typically going from float 32 to something lower, and you need to then start to learn the offset and the range. You don't just simply convert float 32 to float 16. I mean, you can do, but if you're doing things intelligently, you actually want to start thinking about what is the optimal representation that minimizes the drop in accuracy and maximizes the bits and gets the very most out of these bits. And you end up then basically kind of finding these optimal offsets and like scaling factors for the quantization, basically. And again, lots of different approaches. You can do it statically after training. You can do it dynamically after training as well. You can do it during training. So you actually do quantization aware training. So there's a whole research field here that we won't go into, but again, suffice it to say, lots of tools and lots of approaches and lots of packages for doing this. So again, all these libraries we're showing on the left, which each have their unique algorithms and each have their unique features. And again, the hardware that they do and don't work with. So again, it's not a simple one-stop shop for this. It's again, a very fragmented, messy landscape when you're looking to apply these kinds of techniques to your models. And again, just a bit of a representation again of how fragmented this is. We've done a bit of a connection between the bit level that's supported, the techniques that are supported, and the libraries that are supported with these interconnects. And again, you can see that not every library supports every technique and supports every bit level. So again, a very fragmented space in the tooling for compression techniques today. So another approach is tensorization, where we do these tensor decompositions. Again, high level is that we take a large matrix and convert it into a set of low rank weights. Again, I won't go into crazy detail, but suffice to say, there's many different techniques developed in research, and it's a very active field still today. You can do Tucker decomposition. You can do the one ranker decomposition. So with CP, you can do tensor train factorization, TT, and and many others. So again, without going into too much detail, there's a lot of different techniques, each of which work particularly well with certain neural network architectures, with certain training regimes. So a very active research space, and again, no simple solutions here. And again, the tooling is well, in this case, there's not too many packages. One that we're personally big fans of and are working with is Tensorly and Tensorly Torch. So this is definitely the best package out there for doing tensor decompositions with PyTorch. There's also another package I see that does a bit of this as well. But again, Tensorly is definitely a package worth checking out for its ability to do this kind of stuff. And then there's model distillation, as we've talked about already, where you have this teacher model that teaches a smaller student model. Again, lots of different ways of doing this. So you can do, response-based, feature-based, relation-based. It can be done offline or online. A lot of different ways of doing it when you look at the distillation algorithms shown at the bottom. Again, I won't unpack all of it, but I'm just trying to give you a quick visual snapshot. There's a lot going on, and it's very complicated. And again, in terms of the packages, so there are lots of research papers for this, but in terms of like libraries that contain this, the two that we've used are Intel's Neural Compressor, which has a unified API to apply some techniques, and SparseML by Neural Magic also has some off-the-shelf recipes for doing model distillation that we find to be very useful. Of course, there's lots of research paper code and everything, but for kind of libraries that package these together, these are two that we would recommend checking out. So that's compression. Compression is another whole complex world, and to really get optimal deployment, you need to be up to date with this stuff, and you need to know, at the very least, the packages that have the kind of off-the-shelf tools for doing this. So then we go to compilers. Unfortunately, the world doesn't get any less fragmented, probably even more fragmented at the compiler landscape. So what these do is they generate machine-readable code, and they typically take arbitrary Python code and extract a directed acyclic static graph, mathematical graph of all the rate operations that are then expressed in efficient representations, ready for the hardware to compute it, basically. So you go from your high-level code, the compilers extract this into sometimes hardware-agnostic graphs, and then progressively lower this to eventually hardware-specific graphs and assembly for the hardware to run, and so on. The entire process of compilers, we don't need to do a whole compiler course, but basically, compilers are complicated. You first go, from your high-level code, you go through your lexical analyzer, your syntax analyzer, your semantic analyzer. You then generate the intermediate code before optimizing that code, and then you get your target code for the specific hardware before going to assembly, and so on. And every compiler needs to go through this. Every program you ever run needs to go through this process. For anyone that's done a compiler course, then this is Compilers 101. But just thought I'd kind of just show how many steps there are really involved with any compiler that you deal with. Now, in the case of ML, this is actually just a very small snapshot, but there are lots of things going on. And actually, one omission here we should have included on the ML deployment frameworks is Mojo, of course. So there's lots of general purpose compilers and compiler infrastructure. So MLIR, well, LLVM is the compiler infrastructure that's kind of been positioned here since the early 2000s. MLIR is now expanding LLVM to handle multiple levels of representation. And this is infrastructure that's very helpful for building new compilers that are done in this kind of systematic, principled manner. There's obviously GCC, CUDA for NVIDIA, and so on. There's lots of then deep learning specific compilers that have come out. So TensorRT is in NVIDIA. Well, it's kind of this compiler package from NVIDIA for writing high-level graphs and optimizing those down through CUDA. XLA spun out of Google, OpenAI Triton, Apache TVM, Core ML for Apple, OpenVINO, etc. So lots of deep learning specific compilers as well, each of which have their own pros and cons. And also there's increasingly kind of, I guess, deployment-oriented frameworks, which are not necessarily compilers. I mean, or even languages. Mojo is a new programming language that is built upon the principles of MLIR and makes it easy to do compiler-level optimizations in a high-level language. That should really be in the top left as well. There's frameworks like Candle and TinyGrad and GGML, which are really frameworks for building code, but they're a bit closer to the metal, and they're kind of much more focused on high performance, and that they're less, much less so, as with PyTorch and so on, much less about composing high-level functional APIs, and they're much more about writing production-grade deployment-ready applications in these languages that are, a bit further down the stack. Suffice it to say, it's very unclear what is the best compiler to be using for any given application. If you want to be running on Apple devices, GGML is very, very good. TinyGrad looks to be very, very good for AMD devices. Mojo is trying to be good at everything, but very early on in that development. For NVIDIA devices and LLM, probably TensorRT LLM. OpenAI Triton is very good. It's now the default for the PyTorch backend. If it's on TPUs, definitely XLA. So again, there's no simple answers here at all. Each of these compilers shines in different situations. CoreML, probably if it's Apple, or now XML, for example. So again, very, very complex and a lot, there's no single solution here either. And I think it's also worth going into Torch a little bit specifically, just to kind of see how that landscape has evolved as well. So PyTorch is the most dominant framework that's used. The vast majority of research and most new companies entering the space using Torch, but their landscape has been very, very choppy, let's say. I mean, when Torch first came out, it was purely based on asynchronously scheduling kernels on the GPU with no concept of a graph at all. There was then torch.jit, which enabled some tracing, but it required very strong static typing of the code, which was very hard to do. You couldn't even use a union in the type hint, so the code had to be incredibly non-Pythonic in order for any of it to be compilable. There was then Torch Mobile, which made it possible to extract kind of graphs to be run on the edge. TorchFX made it possible to trace functional graphs, similar to our graph compiler, actually, well, our tracer, sorry. But basically, yeah, you can just then trace out pure, fully functional graphs and unwrap all of the high-level nested call stack of the functions and the subfunctions and the classes and so on. And then Torch Compile, which kind of brought together TorchFX, Torch Dynamo, Torch Inductor, and a lot of these things into one place and brought them all together quite elegantly to really have lots of flexible options to take dynamic PyTorch code and bring it closer to being fully compilable as a static directed acyclic graph. And now ExecuTorch, actually, that should also be on here because that was announced a few weeks ago. And that's bringing PyTorch closer to being fully serializable and making it fully deployable without needing the Python session live. And that's obviously really what you need. If you really want to deploy machine learning, ideally you can export it into a representation that doesn't require Python to be spun up, which is, Torch Compile is great, but it still needs Python, and it still leaves some of the dynamism in place if it can't make a graph. Torch Export is all about really making it fully exported from Python and doing so efficiently using the very best compiler technology that's under Torch Compile. So again, even in one framework, it's a very complex landscape of lots of different sub-projects and different teams working on different branches and these kind of weaving in and out of one another and not necessarily all being totally holistically done. So, very, very, very choppy space. And then the hardware, finally, so we have obviously CPUs that have been around for a long time. We then had GPUs come out later on, optimized for graphics. Obviously, from the early 2012 onwards, we started to see these being massively used for AI as well. I think when I started my PhD in 2016, already they were there was obviously cuDNN and things, and they were doing a lot of neural network optimized stuff. But it's really obviously exploded since then with lots of very AI specific initiatives, and NVIDIA now probably seeing itself more as an AI chip company than a graphics chip company. And also all kinds of AI PUs or XPUs, which are other players coming out with very specifically AI inspired and driven architectures. And again, we've just got don't take these kind of high and low with a grain of salt. Obviously, everything's quite complicated, but there's all kinds of great architectures coming out, great hardware devices, I should say, coming out. So there's Gaudi architecture from Intel, Grace Hopper, very promising from NVIDIA. There's TPUs from Google, IPUs, and from GraphCore and several others. There's Cerebrus, there's TensorTorrent, North Pole, Xilinx, Inferentia, Corsair, and many others. I guess the main takeaway here on this slide is that there is a lot of stuff, and there's only more companies coming out and playing a role. Again, there's Grok coming out, there's Samba Nova Systems, there's many basically, and all of these are threatening, or at least trying to threaten, Nvidia's dominance. And again, I think Nvidia's dominance is quite a lot down to their software moat, and I think if things like Triton and Mojo might start to undo that a little bit, then there could be some genuine competition, particularly if there is a genuine bottleneck on fab development, which means that the kind of limited the limited silicon gets more dispersed among more players, and of course then because people need to get access to all of that silicon, there would be a diversification of the hardware vendors, but very hard to see. Like, it's a very interesting space to keep watching though. So bring it all together. So we've talked about how none of these layers, and we should call this, the first layer I called it orchestration, but referring to it as serving maybe makes more sense. So we have these 4 layers we've gone through. There's first of all your model, and then we need to serve it up. We need to kind of handle the API requests coming in and scale up and scale down the hardware and everything. The model itself needs to be modified, really. If you want to really get the best performance, you need to think about compression, because in most cases, the cost accuracy trade-off is not zero compression. You should think about some compression at the very least for most cases. And then, what compiler to use, what compression works with what compilers work with what hardware, and so on. And all of this is a big jungle to try to navigate through. And this is only getting worse. There's new players constantly coming out at all of these levels. There's obviously a ton of players desperately racing to get their own silicon out. I think Meta is still talking about their own silicon. OpenAI are talking about their own silicon. All the big players, AMD, Intel, etc., all racing to get their own, acquisitions, their own hardware acquisitions out to the races. Amazon with Inferentia and Trainium and so on. There's also a lot of new infrastructure coming out. So VLLM is relatively new. Mojo is very new. TensorRT LLM is new. So a lot of stuff coming out there. And again, the problem's only getting worse. TinyGrad as well, relatively new and promising with AMD, etc. So I guess the question is, like, for different user profiles, it's really hard to know where to start. Like, do you want to run it on the cloud? Do you want to run it on the edge? Do you want to have a mix of cloud and edge? Do you want to optimize for cost more, or latency more, or throughput more? And all of these things are incredibly application dependent, and there's no right and wrong answer. And in fact, any given model has many optimal solutions. For one given model, there are many different ways of, for any one given model, it really depends on the application for what you should actually do with it and how you should actually try to think about serving it, because every application has a different requirement to balance these different competing factors, basically. And just to give a bit of a, I'm not sure if these are really exhaustive, but to give a bit of an idea, we've got a few kind of hypothetical case studies. So let's say there's a startup that wants to build an app that counts repetitions of an action or something like this. The main point is that it must run on the edge, and it's very much based on convolutions. So if it needs to run on the edge, we really need to do compression. We need to lower the memory consumption of the model, otherwise it won't run on the edge. And given that it's based on convolutions, these are particularly well suited for doing quantization and pruning when you're doing your compression techniques. So so this is kind of the first thing you might think to do. And again, that's just one thing you do. Of course, you then need to make decisions at every other level of the stack as well. But this is kind of maybe the first priority. Let's assume that there's someone that wants to really lower their latency because they need to make very fast, time series projections, and they've got maybe a large language model or transformer for doing this, but actually the latency is more important than the accuracy, and there's a trade-off to be made here. Well, again, compression is a very good way to lower the latency, as well as compilers and so on as well. But let's assume that it's been optimized for compilers. So then you might want to do tensorization and maybe some knowledge distillation to, assuming the model has many linear layers and it's a transformer, to really get the latency down. Another one, maybe it's a small company that's iterating, doesn't have the compute resources that it needs. It wants to kind of start trying out with some simple model and testing these out. Doesn't have the in-house MLOps. They really favor usability right now over that kind of system stack flexibility. And then you would just say, well, you can just spin up on replicate and go for a serverless option, and it'll take you very little time, and you can go try things out. And then let's say there's a a company that's wanting to use specialized hardware to improve medical image classification. They're really optimized for high throughput. And what you might do in this case, it really depends on other factors as well. But you might want to start doing some customized kernels and also some dynamic batching, for example, to really get their application to handle very large volumes of data in a specialized way, in a way that maybe the kind of existing kernels aren't set up for, and you need to do some customizations to manage the kind of very large volume of data that you want to pass through in single batches. I mean, these are just some examples, but just kind of paint a bit of a picture of whenever there's a given application, the principal priority varies a lot, and the first thing you should work on varies a lot as well, and the optimal recipe to combine changes substantially too. And I think something that's maybe not fully captured by this image, but it's a really important point to get across, is that importantly, and I think maybe the best image to have as a backdrop for this is just this. A really important point to make is that you can't just independently choose what you want to combine together, because, as an example, bits and bytes is a very good package for doing with kind of quantized or quantization aware CUDA kernels, but that combines two. That is compile infrastructure, which is hardware specific. So as soon as you've decided to use bits and bytes, you're locking yourself in to using quantization with CUDA, so that's your compiler defined, and with an NVIDIA device, that's your hardware defined as well. So you've kind of made a decision that basically locks you in three different parts of the stack. Similarly, you might decide, oh, I want to now compress my model, and I've now compressed the model, and it's now 1/3 the size. Well, that changes, and that's at the compression level, but that changes everything for you at the serving level, because now your dynamic batching parameters are totally different. You can probably fit 3 times as many queries per batch as you could before, because the model is now 3 times smaller, for example. And now you need to retweak your Kubernetes parameters. You need to retweak your dynamic batching. So again, your compression and your serving are also intricately linked together, and so on. So, and there's many examples of this, and certain things do and don't work together well. And there's also, sometimes you take one more example. Let's say that you heavily prune your model, so many of your weights are now 0. Well, that's great for CPU, because if the arithmetic intensity goes down, which is what happens when you do pruning, there's kind of less additions and multiplications to be done when you do your map models and so on of the matrix multiplication. But it's same with tensorization. In fact, tensorization is a better example. When you do tensor decompositions, definitely the number of additions and multiplications goes down. And if you're running on a serially executing CPU, then you definitely see speedups, because you just have less additions and it's all stacked together on the CPU anyway. On a GPU that's really optimized for doing dense block gridded multiplications, then having fewer, having this tensorization approach or having a pruned weight doesn't actually necessarily help, because you don't have the algorithms to actually leverage the reduction in arithmetic intensity for hardware that's so heavily optimized for dense parallel computation. So again, even if you've mathematically simplified your model and you've mathematically reduced the number of operations and the additions that need to be done, unless you're thinking deeply about the hardware target, this also might not help. So you can't think about any of these levels of the stack independently, and that's why this is so difficult to really get optimum deployment solutions. So I'll now just talk a little bit about, I want to leave some time for questions and don't want to kind of do too much marketing, but I'll talk a little bit about some of the things we've got coming out. So we, first of all, have released the first version of our database. This is a fully open source, community-driven database of all of the AI deployment tools that we think are relevant and people should be thinking about and people should be using. And this covers all levels of the stack. So that's orchestration, compression, compilers, and hardware. And we have many other sub-labels as well. We're iterating on this quickly. It's relatively basic now, but still, if you go to unify.ai/database, you'll get a quick view of what we've got so far, but that's going to keep changing as time goes on. The other thing is that we strongly welcome and encourage contributions from the community. So if you find a tool that you think we've missed and you think it should be added to the database, you can click the button edit on GitHub, and you can go to our open source database repository and make a pull request and suggest that we add something, or you can suggest an amendment to one of the descriptions if you don't think it's fair. Other things we're going to add here are the ability to compare different cards, the ability, a slightly more hierarchical structure of the cards, and maybe also some kind of recipes and cards that do and don't fit together. And you can then think about kind of putting these together like Lego bricks to some extent, and just kind of seeing what things you can maybe combine together. But just some of the ideas we've got for the roadmap ahead on this. But the main intention is just a resource, and for anybody that's looking to deploy AI models to get an objective perspective on what these different tools are and how you should be thinking about them. We're also working on getting, so we'll be releasing, well, hopefully in February, potentially a bit earlier than that, but we'll be releasing some like case studies and some tutorials explaining some particular use cases and how we've gone about optimizing certain models for different use cases. So we'll have one that's all about compression, and we'll go from start to finish, the whole process of compressing a model for a particular application. We'll do another one where we go through the whole process of writing some custom compiler logic and getting the best compiler infrastructure, and maybe even writing a few custom kernels as well. And one where we optimize the serving infrastructure for a particular application, and so on. And really trying to empower our community with the knowledge and the tools to deploy efficiently and make sense of the noise with all of these tools that are out there. And finally, and most importantly, we're releasing our model hub at the beginning of January, or beginning/mid of January next year. Tentatively got the 11th lined up as the date. And the idea for the model hub is that you have your model that you want to deploy, and you can then compare and benchmark across various different implementations of that model to see which is the most suited for your application. So you can come into the hub and you say, this is how much I can spend per month on API calls. This is how much latency I can afford. This is how accurate it needs to be. And you can kind of define the boundaries of your search space, and we can then provide you with what, based on your selections, what we think is the best configuration possible for you, among many, many options, based on what you've told us. And we can then continue to do this as a service. And as your application changes and the API rate goes up and goes down, maybe the recommended configuration changes because of that, and we can change that for you on the fly automatically. The landscape is an ever evolving thing, so every few weeks probably the optimum solution is different than it was 2 weeks before, and we can keep you on the pulse of that and make sure that you constantly have your models flying, and that we can make sure we bring you the very, very best. And this isn't because we optimize all of the models, it's because we partner with many other great companies who have very optimized endpoints that we can then expose through our benchmarking tool, and you can use these kind of very easily with a single sign-on and compare against them and so on. So this is the idea of the model hub as well, and how we're looking to simplify things for users. And the other thing to say is that it's a community-driven hub. So if anybody wants to upload their own heavily optimized model and add it to the marketplace, then they can do, and they'll get revenue from the users that use it. So if you're very good at optimizing models, then you can make it open source and add it. You can make it proprietary and add it. You can do what you want, but you can upload it to the hub for other people to make use of and build applications on top of. As well. That's another reason why we want to make these videos, to really empower the community to be able to start uploading their own models as well. And this is kind of what's represented here. So again, users build their own recipes. We partner with companies who add in very optimized models into the hub as well. And we can also, add other point solutions based on our own knowledge of how these different optimization tools and deployment tools can be composed together to provide lots of different options among this vast combinatorial search space, and make recommendations for users based on what they tell us they care about for their application. They can be downloaded as API endpoints or Dockerized recipes. So it can be either fully hosted by us through the platform, or you can download it for on-prem execution as well. And the final point, just to leave you with, is a very quick case study. I know we're pushing time a bit, but just to show again the complexity of compression, and just one model that we've optimized as a case study recently. So we have this model that does repetition detection. It's a model from DeepMind. It detects how many times any given action happens in a video. The initial model size, which is 93 megabytes, is very large for mobile phone applications. And off the shelf, the runtime is too slow for real-time processing. It takes 6 minutes on average CPU inference time for a 2-minute video. And ideally, we'd want to be able to process these videos faster than real time. So it needs to at least be 3 times faster. We were able to achieve this, and the way we did it was not a simple off-the-shelf tool. It actually required quite a lot of thought. So first of all, there's a convolution-heavy component in the encoder area. We applied factorizations here, so we did tensorization and got a 2 times speed up with 40% less weights. We then did pruning with PyTorch pruning in some of the weights for 1.8 times speed up. And then we also did dynamic quantization with PyTorch quantize for a further 10% size reduction and a 1.2 times speed up, which combinatorially resulted in 4.3 times speed up with 80% smaller, so only 20% of the weight left at the end. And all of this only reduced in a 1.3% accuracy loss. So again, it's not the case of like you just apply quantization, you apply tensorization, or you apply pruning. You often need to know about these heuristics and what should be applied in what areas to get the best recipes. And this is the kind of thing that we're very good at doing, and is demonstrated in some of the models that we will be adding to our model hub early next year. And again, it's not simple. It was in TensorFlow originally. We transpiled it over to PyTorch with our transpiler. We applied all these PyTorch tools to it. We brought it back to TensorFlow using TF Lite to get it to the mobile device. So using our transpiler, using our knowledge of the tools in the ecosystem and so on. So, quite a lot of moving parts to get these solutions out there into the hub. And yeah, in terms of the kind of roadmap. So again, we've talked about unifying development, unifying and doing deployment optimization. What we've got ahead is, the unified model hub, which we're working on, and then potentially as well looking at doing fine-tuning capabilities as well going forwards. But yeah, so this is kind of the roadmap ahead. But to make sure I leave some time for questions, I'll stop there. Sorry for running over a little bit long. But yeah, thank you very much for listening.
Yeah, thank you very much for this cool overview and presentation about different techniques of optimization. We have some questions. If you have still question, you can use Slando. The link is under the video, and we will start to answer for some of the question what we have. We'll start from you speak about that you start to build database of different tools, and we have one interesting question: how to decide which tool to select?
Sure. So we try to be quite exhaustive. We're only at the beginning now, so we have 106 added so far. But basically, so anything that we would consider using in to optimize a model is definitely something that we add. But also anything that did play an important role in model deployment historically, we also add as well. We actually recently added a kind of flame emoji and so hot and cold tools. If things have kind of been archived and they're no longer being used, we will still add them for kind of archive reasons, but we'll put a cold badge on them. And then for things that we would consider using and things that are actively used today to get state-of-the-art performance, anything like that gets added. Although we try to keep it so that it's kind of a library or tool that is being actively maintained and is somewhat general. So that is a little bit arbitrary. Like if it's just a research paper that's super specific for one particular architecture and it's just some research code, then probably we don't add it. But if it's kind of a properly maintained general purpose library and it's useful for model deployment and optimization, then we do add it. This is kind of how we think about it.
Yeah, and if we speak about users, how they choose some tools between, for example, for model experiments, for CI/CD, for data pipelines, for optimization, a lot of tools. How can you help them to do such choice?
Yeah, sure. So I mean, I guess I would say one thing is that basically, our main focus right now is on optimizing deployment specifically. So there's a ton of different things for kind of, data pipelines, and particularly for kind of model tracking and experiment tracking and all these kind of things. The work we're doing is somewhat orthogonal to those. Take, for example, weights and biases or iterative AI that do, versioning of the weights and the data sets and models and stuff. we don't look at those tools. We look at tools that are specifically about getting the models in deployment after they've been trained and after the kind of at the very end of the MLOps cycle. That's kind of when we come in to get them really flying in production. And so it's kind of orthogonal to a lot of the MLOps tools. And we don't typically index MLOps, like out and out MLOps tools in our database. It's very much about things that are for deployment and that make deployment faster in these kind of 4 categories, basically.
Yeah. Okay. Next question about what's the advantage of EV against Keras 3.0, which has also the same features?
Sure. So the main difference with Keras is that Ivy has a transpiler. So Keras is a high-level set of classes that sits on top of the different frameworks. So part of what Ivy does is similar. Keras basically, well, it has a functional component and then a class component, and the functional component, as it did back in 2015 and 2016, now wraps TensorFlow, PyTorch, and JAX. But you need to write new code in Keras in order to support these different frameworks. With Ivy, you don't need to do that. So just one thing as an example that Ivy can do that Keras cannot is you can take PyTorch, you can take what's it called, Cornea, just this computer vision library in PyTorch, and you can use that library in a TensorFlow project, and that you can do it with one line of code because you can convert code from framework A to framework B. You can't do that with Keras. With Keras, you can write new code that supports different frameworks, but that's all you can do. You can't take code from one to the other. That's the main difference, I guess, among others, which is that we are a bit more exhaustive with our testing. We have more functions and just we've done things, I would say, more deeply, thoroughly, and covered more cases and more frameworks and so on. But the main difference is the transpiler, the ability to convert code.
Yeah. Next one about would you say that compression and pruning of structures is
I would like to think that tech is like that altruistic, but I think when companies are trying to save costs and be efficient, they obviously like to bundle that with sustainability. That's great. Efficiency is always good. Efficiency is good for everything. It's good for your own bottom line and economics and efficiency. But I think companies need to do more. I think companies need to do more than just optimize their efficiency and wave the kind of sustainability banner a little bit. It's kind of how I think about it a little bit. So I guess it's good. The fact that we're now looking to try to make these models much more efficient and much less memory and compute hungry is good, but at the same time that we're doing that, the models are getting much bigger and everything. So I think the vector of growth and the rate at which people are trying to make GPUs faster than ever is kind of growing faster than the rate of us looking to compress them. So I don't know if there should be too much to kind of celebrate, but I think it's a good thing, basically, of course.
Interesting question about K learns from your switching from a PhD student to CEO of the company.
I guess there's not that much overlap. So there's a lot of overlap, which is the purely technical side. Because to be honest, when I started my PhD, I was not a good software engineer. I'd done my mechanical engineering degree, my master's. I did a few hobbyist projects at home, like doing robotics projects and stuff. And my master's project was a bit computer science related. I just kind of taught myself coding on YouTube, basically. And very thankfully, my PhD supervisor, trusted that I'd done enough independent work that he was willing to take a risk and let me do a PhD in computer science, despite having no real formal training in it. And I wasn't really ready, and I learned a ton from my colleagues, and went from someone that had only written a very long Python file to then actually getting some good software engineering design principles and stuff. So I'm very grateful to have been given the opportunity to kind of very quickly learn computer science in a pretty high pressure environment, which was great. And I think I learned a lot about success and failure, I guess. You submit things to conferences, they don't get through. You have an idea, you work on it for a long time, someone else gets the same idea out before you. You kind of need to get comfortable with the constant risk of failure. and be okay with that. And I think you need to be the same as a founder. You need to be quite resilient to a very fast changing landscape and being comfortable with the chaos of constantly trying to make sense of it and remain relevant. So there's a lot of similarities, but I prefer being a founder because I feel I'm quite a social person. I've realized after like many months of solitude in a PhD, and I love talking to people and stuff. So I definitely prefer my new role.
Yeah. Next question about connecting open source tools and proprietary tools.
Yeah. So well, we can't ensure compatibility, and that's why we think carefully about what is and is not compatible. So of course, yes, some proprietary tools are not compatible with open source tools, and that's also why in our database we're looking to add at least some level of kind of indicating what does and doesn't compose well with each other. Yeah, so we don't try to mandate that they compose together. Some things do, like Kubernetes works with everything. It's like very broad orchestration tooling, and the Docker works with every framework and everything. But as I say, bits and bytes doesn't. Bits and bytes is CUDA and it's NVIDIA, and that's it. And we just need to know what they are so we know what the search space actually looks like when thinking about solutions. Yeah. So I can kind of just maybe go through. So are there any So are there any emerging technologies, trends in AI ML that you're excited about? How do you think they will shape the future of the industry? There is one that I'm very excited about. It's a bit kind of in my niche, I suppose. But one thing I do personally think is that AI for compilers is going to be huge. I've been inspired by the work of Alpha Tensor, and also there's some more recent work at DeepMind. I think DeepMind are at the forefront of this kind of research. Although Meta did a paper recently where they applied, we did it in our reading group a few weeks ago, so I'd recommend anyone to go check that out. But Meta did a paper where they applied like Llama 7B to the problem of trying to find the optimal flags for LLVM compilation, and it was able to do that pretty well. And so that is really interesting. There's also the fact that there's very interesting reinforcement learning driven solutions that are very good at searching, massively big search spaces, such as the search space of all matrix multiplication algorithms, and find solutions that are better than human heuristics. And I think compiling high-level mathematical code down into optimal assembly is a massive search space, and it's one that's ripe for optimization with AI. And I imagine a future where things like quantization, model distillation, and compression in general, pruning, etc., but also kind of kernel fusion and tiling and flash attention style insights, all of this could be an implicit byproduct of a higher level optimization loss function, with an AI that understands deeply the assembly language of the particular device and understands deeply the user's requirements in terms of latency, cost, and accuracy, and it just kind of finds the best assembly code possible for this thing. And I just think that's kind of very exciting, because I'm sure that the search space goes a lot deeper than our heuristics have taken us when it comes to kind of our hand-engineered solutions. That's my feeling. I might be wrong there. I'm not really a hardware expert, but that's kind of what I think, because there's so many different mathematical approaches to optimize things and compiler-based approaches to do things that I'm sure the search space for the hardware that we've got, even just the hardware we have today, the silicon we have today, I'm sure we're not even close to like maxing out the performance for these models if we like really looked at the whole search space of assembly code. So that's very exciting to me. Can you share insights or examples from the demos of Lightning Fast applications you've made? Yeah, so that's something that, because we've been working with some companies on this, and at the moment we've not disclosed who we've worked with or what application we've worked with them, but we're planning to release that, and with some videos and some kind of very clear demonstrations of who we've optimized models for and what they're using that for and what the difference is and how that has changed their application in January next year. So suffice it to say that we've been able to get models kind of up to kind of 8 to 10 times faster for some really cool things, like kind of text to video and text to speech and all these kind of things, and that's enabled some really cool applications. But we'll be announcing those and who we've worked with and stuff in the new year. The slides will be shared. I will leave it with me. I can add them to in the description of the video or something like this.
Yeah, we will share the videos and slides
Yeah,
in the coming future.
cool. And then one more. So, what do you think will be the lowest monthly cost to serve and manage? Well, it depends how many API requests you have. So zero if no one's using it, because we'll have scale to zero features as well. So it depends really, but comparable. I mean, so the short answer to that is Unify is not really a competitor with what's out there. Unify, through Unify's model hub, you will be able to query GPT-4, Anthropic, Mistral, any scale, Octo AI. Like the idea is that you can test out whatever's out there already, and you just pay their cost directly. We're actually not looking to charge anyone for this, at the moment. So we wanted to make it really easy for people to kind of use and compare against all of them, basically. So yeah, it depends how many API requests you make, basically. So cool.
Yeah. Cool. Yeah, thank you for answer for all questions. Thank you for all who was with us. Again, thank you for your time and your cool presentation.
Likewise. No, thank you. It was amazing to be here. Honestly, it's such an honor. It's such a vibrant community, and yeah, looking forward to staying in touch, and had a lot of fun.
Yeah, if you will have some more questions, please ask in our Slack channel. And I hope Daniel also will join us in the Slack channel, and we can
Of course.
continue the discussion there.
Sounds good.
Yeah, good. Thank you. Bye.